Okay, and after that I'll write down a piece of code for this quick sort algorithm. Fine. Okay, now see, first of all we will discuss the base idea behind this quick sort algorithm. Let us take this array. Okay, we are having these elements. The array name is A. Index is from 0, 1, 2, 3, 4, 5 and 6. Elements are 7. Total elements are 7. So the basic idea behind this quick sort is what? In this sorting algorithm, we are going to choose one element, key element, or you can say pivot element. Okay, and you can either choose this first element as pivot element, the last element of the array as pivot element, or any random element as pivot element, or you can say the median element as pivot element. There are many techniques to use pivot element. Here in this video I am going to choose this starting of the array, this first element as pivot element. Fine. So let us suppose this pivot element is this 10, first element of this array. Now see, this quick sort algorithm is basically based on the divide and conquer technique. Now in divide and conquer technique, what is the funda? This complete array would be divided into sub arrays. Fine, and this dividing of this array into sub arrays is known as here partitioning. Okay, and that partition method, or you can say partitioning of this array, that processor, that thing is known as, you can say, the backbone of this quick sort. Okay, that is the main funda. How to partition the array, that is the main funda in quick sort. If you know how to partition this array, then you can easily write down the code for this quick sort. Okay, now see how to partition this array. Now 10 is pivot element. Now we are going to partition this array in a way such that all the elements less than this pivot element would be to the left side of this pivot element, and all the elements greater than this pivot element would be to the right side of this pivot element. Okay, and if any element is there which is equal to this pivot element, that element can go either way, to this side or this side. It depends how you are going to implement that logic. Okay, now see how to partition this array. After partitioning, see here we have pivot element, or you can say key element. This is partition 1 and this is partition 2. Fine, and all the values this side would be less than 1, this one. Here the values are, we cannot say that here the values are in sorted order, but this is for sure that all the values to this side would be less than pivot element, and all the values to this side, to the right of this pivot, would be greater than this pivot element. But we cannot say that, we cannot guarantee that these values are in sorted order and these values are in sorted order. That is not a case. Okay, now again we will apply the same funda to this sub array. Fine, and to this sub array we are going to partition. We are going to choose pivot element from this sub array. We are going to partition this again into 2 parts. We are going to partition this again into 2 parts, and we are going to continue this one until we have only one element left. Now if you are considering this 10 as pivot element, see this 10 as pivot element, then all the values less than this 10, how many values are there? See, this 1 is less than this 2, this 9. So these values, sub array, this is another value, you can say 2, this 2, this 9. So these values would be to the left of this 10. Maybe you can say 2, 1 and 11, and now this is our sub array, this is another. Here we have 4, here we have 3. So this is at its appropriate place. No need to sort this 10 now. Here 6. Now see this position, this 10 is at position 3. So this is at its appropriate place. No need to sort this 10 now. Now we are going to apply the same procedure from 0 to 2 and from 4 to 6. This 10 is at its proper place now. Fine. Now see this range, to the left of this 10 you have 9, 2 and 1, or you have 1, 2 and 9, or you have 2, 1 and 9. So these elements can be arranged in many ways. It's not like that you'll always got 2, 1 and 9. It depends how you are going to implement that partition logic. And in the same way to the right also, maybe I'm getting the arrangement 15, 11 and 16. Maybe you are getting the arrangement 16, 15 and 11. Maybe another one is getting the arrangement 11, 15 and 16, like this. Okay, but that is for sure all the elements to the right of this 10 would be greater than 10. All the elements to the left of this 10 would be less than this 10. And same element or equal element, 2 parts. Okay, that is known as partition method, and this is the backbone of this quick sort. Now we are going to take one example and we are going to apply that quick sort on that example. So now let us take this example. We are having 9 elements in an array. Name of the array is A, and index is from 0 to 8. Okay, now we are going to consider this element as pivot element. So pivot element is 7, or you can say pivot element is A of this 0. Fine. So this is, you can say that, lower bound of this array, and this is what upper bound we have. Okay, now simple thing is you have to find out proper place for this pivot elements. such that all the elements less than the 7 would be to the left side, all the elements greater than 7 would be to the right side. So now what you are going to do is, you can say that if any element is this side and which is greater than this pivot element, then we are going to move that element to right side, fine, to the rightmost side you can say. And if any element is this side and if that element is less than this pivot element, then we are going to bring that element to this side. So I am going to take now two variables. One is, suppose here we have start and here we have end. Okay, I am going to move the start from this side to this side and I am going to move this end from this side to this side, right to left and this to left to right. If we are going to move the start from left to right, then obviously we are going to increase this start, we are going to increment this by 1, first of all 0, then 1, 2, 3 like this. And if we are going to move this end from right to left, then we are going to decrement this end, that is for sure. Okay, now what are the conditions? If you are incrementing this start, when you are going to stop this? If you are decrementing this end, when you are going to stop this? You have to find out that condition. Okay, now if you find any element which is greater than this pivot element, at that element you are going to stop this start, otherwise we are going to increment this. Or in another way you can say that if you find any element which is less than or equal to this pivot element, then we are going to increment this until we found the element greater than pivot element. See, now see, start is at this place first of all. Now pivot element is also this and start is also this. Now the 7 is less than or equal to pivot element. Yes, because it is equal to this pivot element. Then we are going to increment this start. Now start is at this place. Fine. Now 6 is less than pivot element. Yes, again increment start. 10, is 10 less than or equal to pivot element? No, we found greater element than pivot element. Then we are going to stop here. Now start is at this place. Fine. Now end. What about this end variable? From here we are going to find out what? An element which is less than pivot element. If element is less than pivot element and which is at this side, then we are going to move that element to this side. Or in simple terms you can say, if you are finding an element which is greater than this pivot element, then you are going to decrement this until you find an element which is less than pivot element. Now see, starting end is at this point 7. Is 7 greater than this pivot element? No, 7 is equal to pivot element. Fine. Greater than, it is not greater than this pivot element, then we are going to stop here only. We are not going to decrement this end. Fine. Now what you will do, now you are going to swap this a of start with a of end, these two values. Now after swapping, what would be the array? Here we have 7, here we have 6. This 7 would be swapped with this 10. Here we got 7 again, here we got 5, 9, 2, 1, 15 and 10 would go there. Now this is our array after first swap. Fine. Here we have AND operator and here we have start. 0, 1, 2, 3, 4, 5, 6, 7 and 8. This is A. Now again check. A of start is 7. 7 is less than equal to pivot element. Yes, 7 is equal to the 7. Then we are going to increment this. 5 is less than pivot element. Yes, again increment. 9 less than equal to 7. No, we got greater element than this pivot element. Then we are going to stop here. Now start is at this position. Now for end, check A of end. Is this element greater than this pivot element? Pivot is 7. Yes, we are going to decrement. This element 15 greater than 7. Yes, we are going to decrement this. Is 1 greater than 7? No, we found an element which is less than pivot element. Then we are going to stop here. Now AND is at this place. Next step is what? You are going to swap this with this. Fine. After swapping, the array would be 7, 6, 7, 5, 9. Sorry, here we have 1, here we have 2, here we have 9, 15 and 10. Okay, and start end pointer is here only and start pointer is here only. Fine. Again apply same funda. A of start, check. Less than equal to pivot element? Yes, increment start. Less than equal to pivot element? Yes, increment start. Is this 9 less than or equal to pivot element? No, it is greater than. So we are going to stop here now. Now at start is at this position. for end, check, because we are going to decrement this end. A of n is 9. Is this greater than pivot element? Yes, then decrement. Now end is at this place. 2. Is 2 greater than pivot element? Pivot is 7. No. Then we are going to stop here only. Now and is at this place. But after that step is what we are going to swap these elements. But here we are not going to swap these elements. Why so? Why so? Because this start variable has crossed end variable. Okay. Start is now greater than end. So now we are not going to swap these elements. Fine. If start is, we are going to follow the procedure of swapping and all until we have start is less than end. At the point we got start is greater than end, then we are not going to swap. Fine. Now next step is what? Now we are going to swap what? This pivot element with this element, the element which is at this position. At this position element is 2, pivot element is what? 7. Now we are going to swap these elements. So after swapping, array would be 2 would go here. Now here we have 6, 7, 5, 1 and here we have 7, 9, 15 and 10. So this is now the array. Now see, this was the pivot element and we got this element here on. Fine. And 0, 1, 2, 3, 4, 5, 6, 7 and 8 and the location for this is 5. So now you can check all the elements which are less than or equal to this 7 are to the left of the side and all the elements greater than this 7 are to the right of the side. Now this is at its, it is now greater than end. Swap these elements, but here we are not going to swap these to decrement this end. And start 7, 6, 7 less than equal to pivot element? Yes. Increment start. Less than equal to pivot element? Yes. Increment start. Is this 9 less than or equal to pivot element? No, it is greater than. So we are going to stop here now. Now at start is at this position. Is this greater than pivot element? Yes, then decrement. Now end is for end, check, because we are going to decrement this end. A of n is 9. Is this greater than pivot element? Yes, then decrement. Now end is at this place. 2. Is 2 greater than pivot element? Pivot is 7. No. Then we are going to stop here only. Now and is at this place. But after that step is what we are going to swap these elements. But here we are not going to swap these elements. Why so? 8. Increase this with finding an element which is greater than this pivot element, then you are going to decrement this until you find an element which is at this place. Fine. Any element which is less than or equal to this pivot element, ten is this 9. See, this was the pivot element and we got this element to the 6, 7. See, this was the pivot element is 2. Pivot element is what? 7. Now we are going to swap these elements. What? Start is greater than end, then we are not going to swap. Fine. Now next step is what? Now we are going to swap what? This pivot element with this element. The element which is at this position. At this position element is 2. Pivot element is what? 7. Now we are going to swap these elements. Now you are going to apply the same same funda on this partition and on this partition till 0 to 4 and 6 to 8. Same from this partition, you are going to choose pivot element. Starting element we are going to choose pivot element, so 2 we are going to choose as pivot element. Fine. Same 2 variable would be there, start from here and end from here only. We will increment this start till we find an element which is greater than this pivot element, and we are going to decrement this end till until we find an element which is less than this pivot element, and then we are going to swap these elements, or you can say exchange those elements. That is why it is also known as partition exchange sort. Fine. Now if I write down this partition method into coding, then how you will write? We have one function, that is partition. We are going to pass a is name of array, lower bound, and upper bound, right? Decrementing minus minus if less than n. Then you will do what? From lower pivot element, and then we are going to swap these elements, or you can say exchange those elements.
हेलो दोस्तों, करने के लिए हमने यहां पे लिखा है। अब कई बार क्वेश्चन आता है कि सर Q को अगर हमने लेफ्ट साइड में बढ़ा रहे हैं तो Q को भी तो स्टॉप करना पड़ेगा, तो क्या यहां पे मैं माइनस इन्फिनिटी लिखूं? नहीं, Q जो है वो P और यहां रुक गया। Q को भी चेक करना है। 15 लेस देन 20 पार्ट्स में डिवाइड हो रही है, प्लस n टाइम सब्स्टिट्यूशन मेथड भी अगर आप सॉल्व करोगे तो आंसर क्या आएगा? n log n। तो आपका यहीं पे रुका रहेगा। आगे मूव करो, 15 ग्रेटर देन 25, नो आगे मूव करो। आगे क्या है? प्लस इनफाइनाइट। तो प्लस इनफाइनाइट पे क्या रुक गया? P रुक गया, यहां से निकल गया P और यहां रुक गया। Q को भी चेक करना है, 15 लेस देन 25, यस यहां पे रुके रहो, क्योंकि Q जो है Q वाला एलिमेंट लेस है तो ये स्टॉप रहेगा। अब आप चेक करो क्या P और Q आपस में क्रॉस कर चुके हैं? क्रॉस कर चुके हैं। जब ये दोनों आपस में क्रॉस कर चुके हैं, मैंने क्या बताया? पाइवट एलिमेंट को Q वाले के साथ एक्सचेंज कर दो। तो देखो 15 आगे आ गया, 20 एज इट इज, 25 ये रहा, और यहां पे जो पाइवट है वो आप एज इट इज 35 को कुछ नहीं करना, वो एज इट इज। तो देखो ये वाला जो देन द नॉर्मल जो है वो एक अनसॉर्टेड एरे लिया है, तो एक वह पॉइंट है। अब ये पाइवट एलिमेंट को हमने यहां पे रिजर्व कर दिया और हमने यहां पे ले लिए दो पॉइंटर, एक वह पॉइंटर P और एक है पॉइंटर Q। अब जो P पॉइंटर है, P पॉइंटर मूव करता है RHS राइट हैंड साइड, और ये रुकता कब है? मतलब ये एक एक करके नहीं, 2 नहीं में, और ये आगे आगे बढ़ता कि क्या P और Q ने इसमें नहीं किया था, लेकिन अब देखो P और Q आपस में क्रॉस कर चुके हैं। Q इधर आ गया, P उधर आ गया। जब भी इस टाइप का सिचुएशन आए क्रॉस करके, तो अब आपको पाइवट के साथ करना है। रेस्ट ऑफ द एलिमेंट सेम 80, इससे जो छोटे हैं वो इधर है, इससे जो बड़े हैं वो इधर है। यानी आपने इस प्रॉब्लम को दो पार्ट में डिवाइड कर दिया, 25 20। फिर पे रुके रहो, क्योंकि Q जो है, Q वाला एलिमेंट क्या, P 25। नो, आगे मूव करो, आगे क्या है, 25 इज द पाइवट एलिमेंट, तो 25 जो है वो मेरा पाइवट एलिमेंट है। 35 को कुछ नहीं करना, वो एज इट इज है। तो देखो ये वाला जो सब एरे है वो सॉर्टेड हो गया। सेम अब हमने यहां पे करना है, 80 आपका पाइवट था, P आपका ये रहा, Q आपका ये रहा, और प्लस इन्फिनिटी यहां। ये एक्चुअल में दो पार्ट्स में डिवाइड हो गया ना, तो ये अलग चल रही है, ये अलग चल रही है। तो सेम यहां पे P 50 ग्रेटर देन 80, नो। नेक्स्ट मूव करो, 90 ग्रेटर देन 80, यस। तो P आपका आप किसको पॉइंट करेगा, 90 को। सेम ऐसे 45 लेस देन 80, यस। Q आपका यहीं पे रुका रहेगा। तो क्या P और Q आपस में क्रॉस हुए, नहीं हुए। तो इस केस में हमने इन दोनों को स्वैप करना है, पाइवट से कुछ लेना देना नहीं है, मतलब इन दोनों को जो स्वैप किया, तो मैं यहां पे लिख देता
In this presentation, I will introduce you to the concepts of doubly linked list. So let's get started. Let's see the definition of doubly linked list. A doubly linked list is different from a singly linked list in a way that each node has an extra pointer that points to the previous node, together with the next pointer and data similar to the singly linked list. So what we have, the difference between a doubly linked list and a singly linked list is that here, in case of doubly linked list, from this presentation onwards, we are starting with the new chapter.
Right? So,
chapter called linked list, and in this particular presentation I will introduce what a linked list is all about and how it looks like. So let's get started. Let's say our target is to arrange the name of the students according to the first letter of their names. This is our target. We need to arrange the name of the students. These are the names available with us. We need to arrange them in sequential order, that too according to the first letter of their names. And this is how the order looks like, right? Of course, the first name must be Alpha. Then we have John, then Mark, Michael, Rock, Smith, Tony. These are the names arranged in a sequential order according to the first letter of their names. Now my question is how to maintain this list in a memory, that is the actual memory. In order to maintain a list in a memory, there are basically two ways available with us. The first one is of course by using array data structure. The other one is using linked list data structure. By using these two ways, we can maintain a list in a memory. These are basically the data structures. We have already dealt with array data structure. Now in this presentation and in the subsequent presentation, we will deal with how to maintain a list using linked list. Arrays have some limitations and disadvantages, and there is no doubt about it. This is very sad. But we will see how linked list overcomes the limitations and disadvantages of arrays. We will see what are the disadvantages and limitations of arrays, and we will see how linked list overcome those limitations and disadvantages in the subsequent lectures. But for now, we will see what are the different types of linked lists we are available with. The first one is of course single linked list. This is the basic type and the first type of linked list. Basically, in single linked list, navigation is forward only. That means we can go in forward direction and we can't go backwards. So navigation is forward only. This is the way we can identify a linked list as a single linked list. When the navigation is forward only, then it is called as a single linked list. But when the navigation is forward and backward, then it is called a doubly linked list. So here in the doubly linked list, forward and backward navigation is possible. We have another type called circular linked list. Here the last element is linked to the first element. As the name itself suggests that this is a circular linked list. So definitely the last element must be linked to the first element. Now, we will discuss what is a single linked list. A single linked list is a list made up of nodes that consists of two parts. Basically, a single linked list is a list made up of nodes. Now, what is a node by the way? This is how a node looks like. This node contains two parts. The one is data and the other one is link. Data part contains the actual data and link part contains the address of the next node of the list. If you ask me how a linked list is made, I will simply give you this answer that a linked list is made up of nodes. Now, we will see how to represent a single linked list. Suppose we want to store a list of numbers. These are the list of numbers we are available with: 23, 54, 78 and 90. For this purpose, I need to create 4 different nodes. Because we have 4 different numbers to store, we need to create a list of 4 different nodes. The first node consists of 2 parts. Basically, a single linked list is a list made up of nodes. Now, what is a node, by the way? This is how a node looks like. This node contains 2 parts. The one is data and the other one is link. Data part contains the actual data. and link part contains the address of the next node of the list. If you ask me how a linked list is made, I will simply give you this answer that a linked list is made up of nodes. Now, we will see how to represent a single linked list. Suppose we want to store a list of numbers. These are the list of numbers we are available with: 23, 54, 78 and 90. For this purpose, I need to create 4 different nodes. Because we have 4 different numbers to store, we need to create a list of 4 different nodes. The first node contains the data 23, the second node contains the data 50, the doubly linked. Definitely, the last element must be linked to the first element. And fourth node addresses 4. And you can see the addresses need not be sequential. This is not an array, this is a linked list. Now of course there is something missing out here. This list is incomplete. Obviously the list has not been created up to now because there is some way to reach the next node of the list, and in order to do that we will store the addresses in the link part of each and every node. How it looks like? Let's see. These are the addresses which we will store in the link part. You can see that the first node contains this address, that is 2000, which is the address of the second node of the list. Isn't that so? From the first node, I can easily reach the next node if I have this address. That is why I have stored this address over here. From the second node, I can easily reach the third node because the address stored here is 3000, which is the address of the third node of the list. And third node contains the address 4000, which is the address of the last node of the list. And last node contains null, which means it is not containing any address. It will simply not point to anything, and it indicates that this is the last node, right? So basically, with the help of link part of the node, we can reach the next node of the list. I'm representing the link between these nodes using these arrows, but you may ask this question that how to access the first node of the linked list. If we have the address of the first node, we can reach the rest of the nodes, right? But how to access the first node of the linked list? In order to access the first node of the linked list, we need a pointer. With the help of pointer, we can access the first node of the list if it contains the address of the first node. I am naming this pointer as head, and in the rest of the lectures we will also see that the name of this pointer will remain head because it is the pointer to the first node of the list. By using this pointer, we can access the first node of the list, and from the first node we can access the second node and so on. So basically this whole list is now accessible. As this pointer contains the address 1000, so I am using this arrow which represents that this pointer contains the address of the first node. After seeing how a single linked list looks like, we'll see how to create a single linked list programmatically and how to perform different operations in single linked list and other linked lists in the same way as we do in the case of arrays. Okay friends, this is it for now. Thank you for watching this presentation. each node has an extra pointer that points to the previous node. So this is an example which shows a doubly linked list, and here is one such node of doubly linked list which has a previous part as well as the next part. In this presentation, let's see the definition of doubly linked list. A doubly linked list is different from a singly linked list in a way that each node has an extra pointer that points to the previous node, together with the next pointer and data similar to the singly linked list. So what we have the difference between a doubly linked list and a singly linked list is that here, in case of doubly linked list, each node has an extra pointer that points to the previous node. So this is an example which shows a doubly linked list, and here is one such node of doubly linked list which has a previous part as well as the next part. Okay, so next pointer points to the next node of the list. And prev pointer points to the previous node of the. But in case of doubly linked list, we have that capability to move backwards. Seems interesting, but since childhood, I have seen a node with just one pointer and data. How to create a node with data and two pointers? Add just one more field to the self-referential structure and it's done. So here is how a singly linked list self-referential structure looks like. Here we have a struct node, of course. The struct node has been declared, where we have a data part as well as the link part. But in case of doubly linked list, we will have two pointers and one data part. One pointer is prev and the other pointer is next. So these are just the names. Obviously you can choose your names, but these names make sense, right? So this is how a self-referential structure of a doubly linked list looks like. Now let's just see how to create a node of the doubly linked. So these are just the names. Obviously you can choose your names, but these names make sense, right? So this is how a self-referential. See how to create a node of the doubly linked list. Obviously, this is the way we would declare self-referential structure for a node, and inside the main function. And here inside malloc function, we have to pass the size of struct node. We got some address, and this address is stored within this head pointer. And then we can simply put null in the prev part out a node. Thank you for watching this. Okay, friends, linked list can be created. Okay, friends, linked list can be created. This is how a node of doubly linked list can be created. Okay, friends, this is it for now. Thank you for watching this presentation. In this presentation, we will discuss how to insert a node in an empty list. So let's get started. In the previous presentation, we have learned how to create a node of a doubly linked list. We have created a node inside the main function. For this purpose, I have allocated the memory for this particular struct node, and this is how it looks like. And we have also learned how to replace the prev part, the next part, and the data part. Now, let's create a separate function for adding a node in an empty list. Instead of adding struct node, so that we would be able to create memory for this particular structure. After this is how it looks like. Obviously, the memory has been allocated. We got some address, and this address is stored within this head pointer. And then we can simply put null in the prev part. Data part can be replaced by 10. It could be any other value. And next part can also be replaced by null. This is how a node of doubly linked list can be created. Okay, friends, this is how a node of doubly linked list can be created. Okay, friends, this is it for now. Thank you for watching this presentation. In this presentation, we will discuss how to insert a node in an empty list. So let's get started. In the previous presentation, we have learned how to create a node of a doubly linked list. We have created a node inside the main function. For this purpose, I have allocated the memory for this particular struct node, and this is how it looks like. And we have also learned how to replace the prev part, the next part, and the data part. Now, let's create a separate function for adding a node in an empty list. Instead of adding node in the main function, I will tell you how to create a separate function for adding a node in an empty list. And this is how it looks like. We obviously add two libraries, that is stdio.h and stdlib.h. And obviously the struct node has to be declared. Then within this main function, you can see over here that I have declared a head pointer which must contain null initially. So this is how it looks like. And after this, I'll simply call add to empty function, which will add a node to the empty list. This is as simple as that. To this function, I have passed head as well as the data. This data is 45 in this case. It could be any other value. And this is how add to empty function looks like, which receives head as well as data. This head is local to this function and data is also local to this function. Within this function, I have declared a pointer temp, and to this pointer we'll pass the address of the node. This is the newly created node and the address of the node has been passed to temp. Using temp, we can replace the prev part by null, the data part by the data which has been received, in this case case it is 45, and the next part can also be replaced by null using temp pointer. Case it is 45, and the next part can also be replaced by null using temp pointer. Finally, we can place the address of this particular node within head as well using temp pointer. And then we can simply return this head back to the main function, which is received by this particular head, which is local to this function. So this null can also be replaced by 1000, which means that this head, which is local to the main function, is also pointing to this particular node. Now, with the help of printf function, we can simply print the data of this particular node. This is the output of this program, which is 45. Okay friends, this is it for now. Thank you for watching this presentation. Which means that this head, which is local In this presentation, we will learn how to insert a node at the beginning of the linked list. So let's get started. Let us assume that we already have this node, right? So this is the initial state of the doubly linked list, and there is a head pointer which is pointing to this particular node. And let us suppose we have this new node, and our target is to add this node in front of this node. We already know that this is the prev part of this node and this is the next part of this node. Now the first thing we should do here is to update the next part of this node so that this node will point to this particular node. In order to do this, we will put this line of code, that is temp next equal to head. We know that temp is the pointer pointing to this particular node. Our target is to add this node in front of this node. In order to do this, the next part of this node must be updated, and this can be updated using temp pointer. For this purpose, I have put this line of code, that is temp next equal to head. We know that head contains 1000, so with the help of this line of code, we would be able to update the next part of this node very easily. After this, of course, we have to update the prev part of this particular node so that it can point to this node. Head prev equal to temp will do the same job. That is, with the help of head pointer, we would be able to update the prev part of this node. Finally, we will update our head pointer so that it can point to this particular node, because this is now the first node of this linked list. After the updation, this is how the resultant linked list looks like. Isn't that so? We have a new node added at the beginning of the list, and head is the pointer pointing to this new node. This is the complete program where we have these two libraries, stdio.h and stdlib.h. Struct node has been declared, and in this main function, we have these three lines of code which have been taken from the previous lecture. Okay, so these are the three lines of codes I have taken from the previous lecture. This helps us in creating a node. After this, we will call this add@beg function, and we will pass head as well as data to it. This is how add@beg function looks like, which receives head as well as data. Receiving head means receiving the node, and receiving data means simply receiving the value. Inside this add@beg function, these four lines of code will help us in creating a new node. After this, we will do the same procedure. That is, we will update the next part of this node first so that it can point to this particular node. After this, we will update the prev part of this node so that it can point to the previous node. And then we will update our head pointer so that it can point to this node. Then we'll simply return head back to the main function. And this is the piece of code which we are already familiar with. And this helps us in printing the data of this particular linked list. And this is the output of this program, that is the pointer pointing to this particular node. Our target is to add this node in front of this node. In order to do this, the next part of this node must be updated, and this can be updated using temp pointer. For this purpose, I have put this line of code, that is temp next equal to head. We know that head contains 1000, so at this node of this particular node, you will be able to update the prev part of this node, where we have these. This helps us in creating a node, a new node. Yeah? This add@beg function, and we will think head means pass head as well as data to it. This is how add@beg function looks. looks like, which receives head as well as data. Receiving head means receiving the node, and receiving data means simply receiving the value. Inside this add at beg function, note. Okay, so these are the 3 lines of code. We will update the next part of this node for the 3 lines of codes I have taken from the previous lecture. This helps us in creating a node. After this, we will call this add at beg function and we will pass head as well as data to it. This is how add at beg function looks like, which receives head as well as data. Receiving head means receiving the node, and receiving data means simply receiving the value. Inside this add at beg function, these 4 lines of code will help us in creating a new node. After this, we will do the same procedure. That is, we will update the next part of this node first, so that it can point to this particular node. After this, we will update the prev part of this node so that it can point to the previous node, and then empty list, and this is previous node. This is the piece simply return head back to the main function. And this is the piece of code which we are already familiar with, and this helps us in printing the data of this particular. The same procedure output of this program is 3445. This isn't that so? We have these 2 libraries, stdio update the next part of this node first. So, and this helps us in printing the data of this particular linked list. And this is the output of this program, that is function, and we will function. These 4 lines of add-back function looks like, and receiving data means simply receiving the value. Inside this add-back function, these 4 lines of code will help us in creating a new node. After this, we will do the same procedure. That is, we will update the next part of this node first, so that it can point to this particular node. After this, we will update the prev part of this node so that it can point to the previous node. And then we will update our head pointer so that it can point to this node. Then we'll simply return head back to the main function. And this is the piece of code. Then we'll simply return head back to the main function. And then we will update our head pointer so that it can point to this node. Then we'll simply return head back to the main function. And this is the piece so that it can point to this data, receiving head, receiving the value. Inside this add-back function, these 4 lines of code will help us in creating a new node. After this, we will do the same procedure. That is, we will update the next part of this node first, so that it can point to this particular node. After this, we will update the prev part of this node so that it can point to the previous node. And then we will update our head pointer so that it can point to this node. Then, and receiving data means simply receiving the value. Think a new node. These 4 lines of code code will help us in creating a new node. After this, we will do the same procedure. Then we'll simply return head back to the main function output of this program, that is 34 and 45. Main function, this is the output of this program, that is 34 and 45. Now let me show the complete code in code blocks. This is the complete code available. You can see over here there is add to empty function, which I have taken from the previous lecture. We have added back function, and of course in the main function the same procedure is written which we have already seen. Now let me just execute this code and see whether we get the desired output or not. You can see over here the output of this program is 3445, and this is all what we want. Okay friends, this is it for now. Thank you for watching this presentation. In this presentation, this is the initial state of the doubly linked list. I took this linked list from the previous lecture to add at the end of this particular list. For this purpose, the step 1 is to traverse the list. Okay, it is important to traverse the list so that we can reach the end node of this list, and then we can update the next part of this node and prev part of this node. For this purpose, I will keep one pointer TP, which will initially point to the first node of this linked list. Later, it will point to the last node of this list. We can do this by adding this piece of code. While TP next not equal to null, TP equal to TP next. This is very simple. Here we are checking this condition. TP next not equal to null. When TP next becomes null, we'll stop our pointer. As simple as that. Right now you can see TP next is not null, so we can move our pointer towards right. And then after that we can check TP next is null. So we'll get outside of this while loop. This is what we want, right? So TP is now pointing to this particular node. After this step, of course, we need to attach a new node to the end node of the list. And that's what we are doing here. We'll first update the next part of this node so that it can point to this particular node, right? For this purpose, we'll add this line of code that is TP next equal to temp. It will put this particular address that is 3000 over here, and that's what we want. After this, we will add this line of code that is temp prev equal to TP so that we can update the prev part of this node. And now it is pointing to this particular node, and that's it. And this is how the resultant linked list looks like, right? We have a head pointer pointing to the first node, and a new node has been, and now it is pointing pointing to this particular node, and that's it. And this is how the resultant linked list looks like, right? We have a head pointer pointing to the first node, and a new node has been added at the end of this list. Node and a new node has been added at the end of this list. This is the complete program, and in this main function, these 4 lines of codes has been taken from the previous lecture. Add to empty function helps us in adding this particular node. Add at beg function helps us in adding this particular node. These 4 lines of codes has been added from the previous lecture, and I'm assuming here that these functions are already available to us. Now after this, we'll call this particular function, that is add at end function, and to this function I'm passing head as well as the value, and this is how add at end function looks, value. This function I'm passing head as well as the value, and this is how add at end. End function looks like. This particular function has a head pointer and a variable data. Head pointer will receive the address of the first node of this linked list, and data variable will receive the value 9. Now, with the help of these lines of code, we would be able to create a new node, which is the node we want to add at the end of this linked list. And this is how the node looks like. And we have a temp pointer pointing to this particular node, and we also have a TP pointer. First, using this line of code, we will be able to store this address within TP. Now this pointer is also pointing to this node, and using this piece of code, we would be able to update our TP so that it can point to the last node of this list. Finally, we will update the next part of this node so that it can point to this particular node, and then we will update the prev part of this node so that it can point to this particular node. As simple as that. Finally, we'll return head back to the main function, and here this piece of code will help us in printing all the values of this particular list. Finally, we'll return head back to the main function, and here this piece of code will help us in printing all the values of this particular linked list. So the output of this program is 34, 45, and 9. Beg from the 34, 45, 9 and node, and now it is pointing to this particular node, and that's it. And this is how the resultant linked list looks like, right? We have a head pointer pointing to the first node, and a new node has been added at the end of this list. This is the complete, right? We have a head pointer pointing to the first node, and a new node has been added at the end of this list. This is the complete pointer and a variable data. head pointer will receive to this particular node, and then we will update the prev part of this node so that it can point to this particular node. As simple as that. Finally, we'll return head back to the main function, and here this piece of code will help us in printing all the values of this particular linked list. So the output of this program is 34, 45 and 9. Now let me show the complete code in code blocks. You can see over here I have taken these functions add to empty and add at beg from the previous lecture. I've added this new function to this program, that is add at end, and in this presentation we will learn how to insert a node in between the other nodes. So let's get started. Let us suppose this is the initial state of the linked list, and our target is to insert a node after the given position. Let us suppose that we need to add a new node after position 2. Our target is to add a new node after position 2. For this purpose, I'm assuming here that this is position 1 and this is position 2, and our target is to add a new node over here at this point. Okay. For this purpose, of course, we need a new node, and there must be a pointer pointing to this node so that we can reference it. And we need a pointer pointing to the second node of the list. This is important. We need a pointer pointing to this particular node so that we can do the updations. It is important that we keep a pointer over here as well as here. First, we will keep a pointer temp. This particular pointer is initially pointing to this node. Later, it will point to this node. We can do this by putting this piece of code. You can see over here, I have kept one position variable, which is storing this value 2. Because we need to add node after position 2. That's why I kept this position variable. And this position variable will help us in moving a temp pointer. The movement of this temp pointer depends upon this position variable, let me tell you. That's why you can see over here in this while loop, I'm checking this condition. Is position not equal to 1? If it is the case, then we can move. Otherwise, we'll get outside of this loop. When position becomes 1, we will get outside of this loop. In this while loop, you can see I'm moving the temp pointer towards right. And it totally depends on the position variable. Here, position variable is decremented. It is clear from this piece of code that when position variable contains 2, then our temp pointer will move 1 step forward. If it holds 3, then our temp pointer move 2 steps forward. And this is very simple to understand. And this is very simple to understand. Later, we will keep another pointer so that it can point to this particular node. We should always remember that temp2 will always point to the node given after the node pointed by the temp. That's why here I have written temp2 is equal to temp next. Now you can see over here that temp2 is pointing to this particular node. Now everything is set. We just have to add this node in between these two nodes. And these pointers will help us in doing the same. First, we will update the next part of this particular node using this line of code. Temp next equal to new p. Using this line of code, we would be able to update the next part of this node so that this particular node will point address part of this node, so that we need to update the person putting this address 3 resultant linked list. So you can simple. That's why here this is the resultant linked list, so data and position. Here you can see 3 pointers are declared: new p, temp and temp2. We know the meaning of all these and the of code as well as this piece of link, the addition of a node at the end of the list. That's why we have to consider that case separately. For this purpose, after this while loop, we will check this condition. If temp next is equal to null, that means if we reach the, we must have to update the next part of the last, keep this piece of code, and that's all. Now let me show the complete code in. So after post function has been called to this function, we want to insert node over here. For this purpose, we will keep a temp pointer. Initially, so it is clear that our code is working fine. Okay friends, this is it for now. Thank you for watching this presentation. A node before a specific position. Let's say we want to add node before piece of code. We will move our temp pointer to pointer pointing to this particular node. We have to consider this case where we need to add a node at the beginning of the list, right? For this purpose, we will replace this piece of code by this piece of code. If position is equal to 1, then head equal to add at beg head comma data. We just have to call this add at beg function, that function which we have already seen. This function, if position is equal to 1, which means we want to add the data in front of the first node, and then has been added. You can see the result over here. 25 has been added. In this presentation, these 2 pointers, head and ptr. Head is initially holding null and p meant for the node 2. That's why I plus 1 is written, which means that we will receive this particular address of this node, create list function, and that element for the node 1. Let's say it is 23, 78 and 98, right? First element is 23, 78 is the second element, returns 0, right? Null has been simply returned back to the main function and nothing will node of this list, and we have 3 nodes in this list, right? Our target is to delete this particular node. For this purpose, I'll keep one pointer temp. This is the traditional old method, right? To keep a temporary pointer so that we can delete the node. And this is required because we have to move our head pointer towards right. And if we move our head pointer towards right, then we will lose the reference to this particular node, right? That is why temp pointer is required. So we will keep a temp pointer so that it can point to the first node of this list. And of course, we need to move our head pointer towards right. And we can do this by putting this line of code, that is head equal to head next. After this, we can call free function to delete this particular node. To this free function, we have to pass temp, that is the address of the first node. After this, of course, we need to assign null to temp as well as null to this particular pref part of this node. And this is the resultant linked list so obtained. There is one more method in order to delete the first node of the doubly linked list. We can also do one thing. We can simply move our head pointer towards right without keeping a temp pointer. Now, why I'm doing this? In case of doubly linked list, we always have the reference to the previous node. That means we always have an address of the previous node. You can see over here, we have this address 1000 already. If we move our head pointer towards right without keeping temp pointer, we can still access the first node. And if we can access the first node, we can delete the first node. For this purpose, we just have to pass head prev to the free function. And that's it. After this, we just have to update the prev part of this node. For this purpose, head prev equal to null has to be written. And this is how a complete linked list looks like after deleting the first node of the list. For this purpose, we just have equal to head null to this particular free function. We have to pass temp, that is the address of the first node. After this, without keeping temp pointer, let me show the equal to null has to be, and that's it. After this function add, now let me show the complete add to an entire list. And you can see over here in the main function, first these three functions has been called, which will create our linked list. After this printf function has been called, which will print this message before deletion. We just create the next part of this node so that it all the elements before deletion. Last node of temp pointer, which must point to the first node initially. Then later, temp pointer towards right node, this particular condition. Finally, you can see the temp to null over here. That is why temp is stopped over here. Now, we will keep another pointer, that is temp2, so that it can point to this particular node. That is the node which is just before the node we want to delete. You can see over here, temp2 is now pointing to this node. After this, we will adjust the links and then we will delete this node. First, we will update the next part of this node so that it must contain links, and then we will delete this node. First, we will update the next part of this node so that it must contain null, because this is going to be the last. Node of the list, right? So null must be placed over here. After this, we will place null over here, and that's it. This is the resultant link. After this, we will place null over here, and that's it. That's it. This is the resultant link. We have this and be able to update the elements remained, that is 34, 45. 9 is deleted from the doubly linked list. So our code is working fine. Okay friends, this is it for now. Thank you for watching this presentation. List. That means 34, 45 and 9 will get printed on the screen before deletion, right? Then
सो तो फ्री फायर में एक्सप्लेन यार है। उसके बाद में गाइस जैसे कि आप स्क्रीन पर क्लिक आउट, उसके बाद में राइट के निशान पर क्लिक आउट कर देना, क्लियर कर देना है। उसके बाद में यहाँ पर सेटिंग में सर्च बार पर आपको मॉडिफाई पर क्लिक आउट करना है, वाले प्रीफेड नेटवर्क टाइप इस पर आपको क्लिक आउट करना है। यदि आपने यहाँ कर देना है, उसके बाद आपको 5G सिलेक्ट कर लेना है। उसके बाद में सारी यहाँ पर सेटिंग को गाइस यहाँ पर कोई भी आपको डिजनेटिव प्राइवेट डीएनएस पर क्लिक आउट करके आउट कर देना है। देन गाइस बिना टाइम वेस्ट किया,
हेलो दोस्तों, मेरा नाम है चेतन। यहाँ पर वीडियो सेटिंग आप इसके बाद जिस भी सिम में आप नेट चलाते हो, मोबाइल डेटा चलाते हो, उनके ऊपर आपको क्लिक करना है। ओके, इस तरह से। इसके बाद गाइस यहाँ पर आपको एक वाला ऑप्शन मतलब एक ऑप्शन मिलेगा एक्सेस पॉइंट्स नाम का। ओके दोस्तों, आपके मोबाइल के अंदर एपीएन का भी हो सकता है। ओके, ऑप्शन तो एक ही रहेगा, एक्सेस पॉइंट नाम हो एपीएन हो। ओके, इसके ऊपर क्लिक करेंगे। इसके बाद गाइस यहाँ पर थ्री डॉट के ऊपर क्लिक करेंगे आप। ओके, क्लिक करने के बाद गाइस यहाँ पर आपको रिसेट कर देना। ओके, एपीएन सेटिंग को आपको रिसेट कर देना है। ओके, इतना करने के बाद गाइस यहाँ पर आपको दूसरी सेटिंग बताता हूँ। ओके, तो यहाँ पर आपको क्या करना पड़ेगा, यहाँ पर आपको क्या करना है, यहाँ पर आपको सर्च कर लेना है। ओके, तो यहाँ पर आपको क्या सर्च करना है अपने मोबाइल के सेटिंग में, यहाँ पर आपको सर्च करना है प्राइवेट डीएनएस। ओके, तो यहाँ पर आप इस तरीके से प्राइवेट डीएनएस सर्च करेंगे। तो दोस्तों यहाँ पर आप प्राइवेट डीएनएस सर्च करेंगे ना, तो यहाँ पर ऑप्शन मिल जाएगा प्राइवेट डीएनएस का। ओके, तो दोस्तों मेरे को मिल चुका है प्राइवेट डीएनएस करके लिखा हुआ। ओके, तो इसके ऊपर मैं क्लिक कर देता हूँ, आपको भी क्लिक कर देना है। ओके, सिंपल है। ओके, क्लिक करने के बाद यहाँ पर ऑफ रहेगा या कोई दूसरा ऑप्शन सेलेक्ट है, तो आपको क्या करना पड़ेगा, इसको आपको ऑटो सेलेक्ट कर लेना। ओके, ऑटोमेटिकली के ऊपर आपको सेलेक्ट कर लेना। ओके, तो यहाँ पर मेरे में ऑलरेडी ऑटो है। ओके, तो आपको इस तरह से ऑटो सेलेक्ट कर लेना। इसके बाद गाइस यहाँ पर आपको एक सेटिंग कर लेनी है। ओके, इसके बाद आपका प्रॉब्लम है वो यहाँ पर फिक्स हो जाएगा, सॉल्व हो जाएगा। तो आपको हेलो दोस्तों, मेरा नाम है चेतन। वेलकम टू माय न्यू वीडियो। दोस्तों आज की इस वीडियो में मैं आपको बताने
ஏய் 2 மேட்ச் எவ்வளோ இருந்தாலும் அனுப்பிச்சுட்றா. ஒரு எப்படி இருந்தால் ஒரு 3 4 அதுமாரி. ஒரு 3 4 அதுமாரி.
Lucia,
யூடியூப்ல உங்களுடைய வீடியோஸை வைரல் ஆக்கிறதுக்கான
no OTG, no USB 4 port hub and no any Bluetooth converter, but this is wireless setup. हेलो यूज़ करने वाले हैं वो मैं आप लोगों को बता। तो यूज़र मैनुअल और तो भाई रखते साइड में, यहाँ पे ओनली सेकंड के लिए। तो यहाँ पर देखो, यहाँ पे यूरो गेम्स करके हमारे पास एक ऑप्शन आ गया ब्लूटूथ का, तो यहाँ पे हम इसे भी पेयर कर लेते हैं। एंड जैसे यहाँ पे पेयर क्या कनेक्ट हो गया, तो यहाँ पर देखो हमारा माउस कर्सर भी आ चुका है। तो यहाँ पे हमारा सक्सेसफुली कीबोर्ड एंड माउस दोनों ब्लूटूथ के साथ कनेक्ट हो चुका है वायरलेसली। एंड यहाँ पे हमने किसी भी USB 4 पोर्ट का भी यूज़ नहीं किया और साथ में ना ही OTG केबल का यूज़ किया है, बट फिर भी यहाँ पे हमारा कीबोर्ड एंड माउस सक्सेसफुली वर्क कर रहा है। एंड अब यहाँ पे हम लोग गेम प्ले करने के लिए पांडा माउस प्रो का यूज़ करने वाले हैं। एंड पांडा माउस प्रो का यहाँ पे बहुत ही बेस्ट वर्जन आ चुका है 2.1.0 वाला, और इस वाले वर्जन में आप लोगों को ऑन पांडा माउस प्रो एप्लीकेशन एक्टिवेशन सपोर्ट देखने को मिल जाएगा। जैसे यहाँ पे एंड्रॉइड 11 एंड लोगों को बताने वाला हूँ। ये हमारे पास है A50 सैमसंग का फ़ोन है, और यहाँ से आप देखो यहाँ पे दे रहा स्क्रीन में ऑन कर ऑटोमेटिक जितना भी पैच कमांड है वो सब का भी झंझट यहाँ पे ख़त्म हो चुका है। ये ऑटोमेटिक एक्टिवेट हो जाएगा। अब हमारा एक्टिवेशन हो चुका है कंप्लीट, और गेम को ऐड कर लोगे, मतलब ये जो लाइसेंस वाला की मैप एंड उसके बाद करेंगे गेम प्ले। तो यहाँ पे मैंने आप लोगों को बताया कि एक बार पिन कमेंट जरूर से चेक कर लेना। प्लस पांडा माउस प्रो का जो लेटेस्ट वर्जन है उसका सेंसी बहुत ही ज़्यादा अमेजिंग है। और यहाँ पे देखो अभी तो हमारा ये डिफ़ॉल्ट सेटिंग है, डिफ़ॉल्ट सेंसिटिविटी है। तो सबसे पहले हम यहाँ से गन इक्विप कर लेते हैं, एंड उसके बाद यहाँ से हम लोग सेंसी को थोड़ा बहुत एडजस्ट करेंगे। उसके बाद हेडशॉट पे प्रैक्टिस करेंगे। इस मेथड को यूज़ करते हुए आप लोग चाहो तो अपने फ़ोन को अपने टीवी से या फिर मॉनिटर से कनेक्ट भी कर सकते हो और बड़े स्क्रीन में गेमिंग का एक्सपीरियंस कर सकते हो। तो आप लोग एक बार मुझे कमेंट करके ज़रूर बताना कि अगर आप लोगों को ये वीडियो चाहिए दूंगा। तो यहाँ पे हम कर लेते हैं सबसे पहले अपने सेंसी को एडजस्ट। यहाँ पे मैं बटन ऑब्जर्विटी को थोड़ा बहुत रखता हूँ जिससे आप लोगों को पता चले कि यहाँ पे ये फेक वीडियो नहीं है। ओके, तो यहाँ पर देखो सबसे पहले तो ये परफेक्ट वर्क कर रहा है। यहाँ पे हमारा सेंसी भी एकदम नेक्स्ट लेवल है, और हेडशॉट तो आप लोग यहाँ पे स्क्रीन पे देख ही सकते हो कितना ही नेक्स्ट लेवल लग रहा। एंड इसी के साथ हमारा यहाँ से प्रैक्टिस सपोर्ट करो ही मत, जितने भी फेयर बंदे हैं, फेयर गेम प्ले करते हैं, फेयर वीडियोस बनाते हैं, उन सभी को सपोर्ट करो। ओके, मेरे अलावा भी बहुत सारे बंदे हैं जो रियल कंटेंट बनाते हैं कीबोर्ड एंड माउस के रिलेटेड, उन सभी को आप लोग सपोर्ट करो। ओके, और हो सकता है आप लोग फ्री फायर के साथ साथ अगर कोई और भी गेम प्ले का वीडियो देखना चाहो तो वो भी मुझे कमेंट करके ज़रूर बताना। ओके, तो मैं उन सभी पे भी वीडियो बनाने का ट्राई करूँगा कीबोर्ड एंड माउस से गेम प्ले करने का। ओके, तो यहाँ पे अगर आप लोग इसको ट्राई करना चाहते हो तो ये 100% ये रियल है, आप लोग इसको ट्राई कर सकते हो। कीबोर्ड माउस लगा के अपने फ़ोन में पीसी का एक्सपीरियंस ले सकते हो। ओके, बस ज़रूरत है तो आप लोगों को प्रैक्टिस करने का। आप लोग नेक्स्ट लेवल प्रैक्टिस करो। प्रैक्टिस करने के बाद आप लोगों का गेम प्ले जब इसमें इम्प्रूव हो जाएगा तब जाके आप लोग एक कोई सा भी कन्वर्टर ले लेना ब्लूटूथ। ओके, यहाँ पर देखो ये सोनिया बना, उसके बाद मैं डायरेक्ट नीचे कूद गया कि भाई ऐसा ना हो कि वो मुझे मार के फिर से जिंदा हो जाए। तो यहाँ पे इसका किल तो मुझे आ गया, बट फिर भी मैं आप लोगों को बता रहा था कि अगर आप लोगों को इसमें गेम प्ले आपका अगर इम्प्रूव हो जाए, नेक्स्ट लेवल लगने लगे हेडशॉट, तब जाके आप लोग एक ब्लूटूथ कन्वर्टर ले लो। उसमें आप लोगों का गेम प्ले और भी जॉड लेवल हो जाएगा। और लाइफ में अगर आपके पास पीसी लेने का बजट हो गया और अगर आप लोग पीसी ले लेते हो तो भाई आपका गेम प्ले हैकर लेवल होने से कोई नहीं रोक सकता। एंड यहाँ पर तो मैंने फर्स्ट बंदे को बहुत ईजी मार दिया और सेकंड बंदे को मारने में बहुत ही ज़्यादा स्ट्रगल करना पड़ा, बट फिर भी यहाँ पे इसको हेडशॉट के साथ फिनिश किया। एंड अब यहाँ से मैं जाता हूँ डायरेक्ट जोन के अंदर। एंड जोन के अंदर जाने के बाद भी आगे मुझे एक बंदा मिलता है, एंड देखो उसके साथ क्या हुआ। और इसी के साथ आज
और यहाँ पे गाइस देख सकते हो, ये रहा मॉनिटर, ये देख सकते हो, ये वाईफाई भी है अच्छा, नहीं तो नीचे कर लो, में उसे अच्छा बोलेंगे। और इतना कम यहाँ पे ये लोग कनेक्शन नहीं दिया था, ठीक ना। देख सकते हो भाई इसके अंदर वाईफाई भी है। बहुत सारा पीसी ऐसा होता है ना जिसके अंदर मतलब वाईफाई डाउनलोड कर सकते हैं ना खेल सकते हैं।
Hi students, welcome back. Let's continue with the B trees in DBMS. So in the previous video, I explained the concept of the B tree. Now let's have a look on the example of the B tree. So I need to create a B tree. Okay. So the B tree, the order they are given it as a 4. Let's take the order is a 4. 4 is nothing but the degree of that B tree. Means each node can have 4 children and the 3 keys. Each node, whatever it is there, it can have the 4 children, and the minimum number of keys should be the 3 only, because if n children are there, n minus 1 keys will be there. That is a concept. What? Hi students, welcome back. Coming to the next concept in the database management system is the B trees. So far you had seen the B trees concept in the data structures. So just like in the data structures, in the database management system also we are using the concept B trees. Hi students, welcome back. Let's continue with the database management system. The next topic in this subject is the B plus tree in database management system. So what is this B plus trees? It is a data structure that we know that, which is used to implementation of database index. So just like in the data structure, so here in the database, these B plus trees are used to implement database indexes. So that's why we call it, it's one of the multi-level indexing, so which is used for the database indexes. It is a balanced binary search tree. It follows the multi-level index format. So that we already know that, which is following the multi-level index format. In B plus tree, leaf nodes denotes actual data pointer, whatever the leaf nodes consisting of, that leaf nodes is give the actual data pointers. Okay, so it also ensures that all leaf nodes has to remain in the same length, height. All leaf nodes remains at same height. Okay, so the leaf nodes are linked. Here one more concept, when compared to the B trees, in the B plus trees, the leaf nodes are linked using linked list. Therefore, it can support the random access as well as the sequential access. So not only the sequential access, it also supports the random access. So the when compared to the B trees, B plus tree occupy a little more space than B tree, because it also have the information regarding the linked list. One node is connected to the another nodes, so that node is already repeated. So that we see, anyhow we will see in the example. Let's have a look on the characteristics of the B plus trees. Characteristics. Data records are only stored in the leaves. Or only stored in leaves, means the leaf nodes. So whatever the leaf nodes consisting of, that is the actual data pointers. And next, internal node stores just keys. and this is an internal node.
That is why I am going to take order 5, and these are the elements, and we are going to create a B plus tree. So if order is 5 maximum, so in this video I am going In this lecture, we are going to talk about tree data structures. See, what is a data structure? It is basically a way to organize the data in a manner such that we can process the data efficiently, right? So basically data structures are having two categories. One is linear data structure and second one is non-linear data structures. So we have discussed arrays, linked list, queue and stacks. These are linear data structures. Like, see, this is array, how we are going to represent logically, how we are going to represent all the four type of data structures, that is this thing. This is linked list, this is stack and this one is queue, right? Stack is following LIFO structure and this is following FIFO, right? This thing we have discussed already in the previous videos. Fine. Now, tree and graph both are non-linear data structures. See, linear data structures means here the data is arranged, you can say, in a sequential form, one after another, right? And non-linear means the data is having multiple levels, you can say. It is a form of hierarchy. Linear data structure is having only one level, right? But non-linear data structure is having multiple levels, right? The data is stored in sequential manner, or which is going to form a special ordering, some sort of ordering, you can say. But in non-linear, the data is in the form of hierarchy, you can say, right? The difference between linear and non-linear data structure we will discuss in a separate video, right? So now, what is a hierarchical data? See, you can take an example of a college employees. Fine. See, here at this level, maybe you have the director, and below this, 3 persons are also there. Here you can say A, and this one is B, C and D. You can say this one is maybe director, or these are having dean or principal or something like this. These are going to directly report to the director. Below these, maybe we are having, below this dean, maybe we are having HODs, you can say, right? Manager or something like this. If you are taking an example of a company, here you can consider CEO of the company, manager, assistant manager, team lead and something like this, right? So here you can say E and F. Below HODs, we are having some faculty members, right? So these faculty members are going to report to HOD, HOD is going to report to dean, dean are going to report to the CEO. This is what a hierarchy. It's not like that faculty is directly going to report to the director of the college. So here I have added some more nodes. So this is what a data, this is what data items which are having hierarchical relationship among them, right? So you can say tree is what? Tree is basically a non-linear data structure which is going to simulate this hierarchy. Tree is basically going to represent this hierarchy, or you can say tree is used to represent the data items which are having hierarchical relationship between them. So now this is what the logical representation of tree in data structure. See, you have to figure it out in which context you are discussing the tree. Tree in the context of graph theory or in the mathematical form, or tree in the context of computer programming or data structure. Because in that case, in the graph theory, we are considering that tree is what? It's an undirected graph which is connected and acyclic, right? But here when we are discussing the tree in the form of in the context of data structure, here we consider that tree, this is having a direction. See, here if this is a tree, in that case you can go from A to B, but you cannot go from B to A. So tree basically grows from here top to bottom. We can go from B to E, F. You cannot go from E to B. Sorry, F to B. So this is, you can say, a direction, right? Somewhere it is represented with directions and somewhere it is represented without directions. But if you represent it without direction, then also the rule is what? The condition is what? You can go from top to bottom. You can go from A to B, A to C, A to D, but you cannot go from C to A. This is the case. So by default, it means the direction is from here to here, from top to bottom. And if you compare this tree with the actual tree, then there you can say that tree basically grows from that ground into the air. We have roots, we have branches, we have leaves, right? But this basically grows from top to bottom. So when you can say flip that actual tree upside down, then here you will have roots, then you can say we have branches and leaves. So here in this tree also, this is known as what? Root, right? And these are known as nodes, right? Nodes means which are going to store some information. So this is going to store some information. Here I'm represented this tree of that college hierarchy. So it is having person name or something like this, or person name and designation of that person, right? But here I'm just writing A, B, C, D, right? So the tree, the nodes can have numbers also, 1, 2, 3, 4. The nodes can have characters also. The nodes can have strings also. But the main thing is what? Nodes are having some information. So how can you define a tree? See, tree is what? It can be defined as a collection of elements, or here we call not elements, here we will call nodes, right? In array we call elements, in linked list we are calling nodes, and here also this is what known as node, because this is containing information as well as link to the next one, link to its, you can say it is what? Successor of this node, right? So this is what a node. So it is what? A collection of nodes which are linked together to simulate a hierarchy. This is what a tree. It is a non-linear data structure. Fine. Now we will discuss some basic terminologies used in tree. Fine. First is what? root of a tree. Root means the topmost element, right? Or you can say root, this is not having any parent. The node which is not having any parent, that is known as root node of the tree. The topmost element or the first element in the hierarchy, that is known as root. So here in this tree, root is what? A. Nodes. Node is basically what? Which is going to store some information, right? And also containing link to the another node, right? So now here you can say this elements of this tree are known as nodes. Elements on this tree are A, B, C, D, E, F, G, H, I, J, K, L, M. These are what? Nodes of this tree. You can take any node. I am taking G. Find out the parent node of this one. So find out the immediate predecessor. Immediate predecessor is C. So this is what? Parent of G. Now what about A? Is there any immediate predecessor of this node, previous node? No, this is the first node only. So root is not having any parent node. Now what is child node? So child, you can say the immediate successor of a node is known as child of that node. See, now what about A? If you say what is the child of A, so the immediate successor means the next nodes. Immediate successor is B also, C also and D also, right? After A, the immediate nodes are B, C and D. We can go to B, C and D after this A. So these are immediate successor. It means you can say B, C and D are children of A, right? Here you can say what about L? Is there any immediate successor of this node? Immediate successor means the next one to L. No, we don't have. It means L is not having any child, right? So these are containing what? Parent-child relationship. Also grandparent also. See, here you can say this C is what? Child of A, but C is what? Parent of G. So what you can say? This A is what? Grandparent of G. So here I have written nodes, example of a parent node also, child node also, right? Now we will discuss what is leaf node and non-leaf node. See, this L, I have told you this L is not having any child. So the leaf node is what? The node which is having no child, that is known as leaf node, right? So here in this case, leaf nodes are, see, I is a leaf node, J and K, and F is also leaf node, L and M are also leaf node, plus H. These are leaf nodes which are not having any child. Plus leaf node are also known as external nodes. You have to take care of this thing, external nodes, right? So now what is non-leaf node? Which is having at least one child, right? So all the other node except leaf nodes are known as non-leaf node, as well as these are known as internal nodes. So here non-leaf node are A, B, C and D also, plus E and G, right? These are non-leaf node and you can say these are internal nodes. Now next is path. See, if I ask you how you can go from A to L, right? You will say from A to C, then C to G and G to L. So this is what? This is what a path, right? First of all, this edge and this edge, right? See, edge is what? Link between two nodes. These are nodes and the link between A and C is what? This one. So this is known as an edge. So path is what? You can say it is a sequence of consecutive edges from source node to destination node. If I am asking you the path from B to J, then the path is what? From B I will go to E, then from E to J. So path is what? BE and EJ, these two edges. So this is what known as a path, sequence of consecutive edges from the source node to the destination node, right? Now we will see ancestor and descendants. See, ancestor is what? Simply in simple terms you can say here in this tree, if you can go from a node A to B, it means, see, like this one, if you can go from this A node to B node, right? And see, one more thing you need to take care, these links are unidirectional, not bidirectional. I have told you earlier also, right? So now here A is what? Ancestor and B is what? Descendant. Fine. And if you want to write down the formal definition, then you can say ancestor of a node is any predecessor node on the path from root to that node. See now, if I ask you ancestor of L, then what you will say? Ancestor of L. First of all, check out the path from root to that node. So from root is A, root to L, the path is this one, this and this one, right? So ancestor is what? Any predecessor node. Predecessor means the previous ones. So predecessor node of L is what? G also, C also and A also, the predecessor on this path only. So ancestor of L is what? A, C and G. Both, sorry, the three are ancestor of L, right? Now, if I ask you what is ancestor of H, it means find out the path from root to H, this one and this one. So ancestor of H is what? On this path, what are the predecessor of H? D and A. So A and D are ancestor of H. Fine. So now next is descendant. Descendant is what? Any successor node on the path from that node to the leaf node. See, with example, if I ask you what is descendant of C, first of all find out the path from that node, means from C to leaf nodes. So from C, here I can go to G, after that I can go to L, I can go to M also. These are leaf node, we have reached to the leaf node. Fine. So these are two paths. Means, so now any successor node, successor means after C on this path, successor node are G, L and M. So now here G, L and M. All the three are what you can say descendant of C. Now what is descendant of B? Right, find out the path from B to the leaf node. So F is also leaf node, so F is also descendant of B. Now path has this one, this one, this one and this one, right? So all these are descendant of B. E also, I also, J also, K also and F also, right? So these are descendant of B. See, now if I ask you what are the common ancestor of G and H? Ancestor means you have to find out the predecessor node on the path from root to that node. Now ancestor of G are what? A and C. Ancestor of no, see the parent of F is what? So from G you need to check out the path to its leaf. Discussed it. See, degree of F is also 0. Now degree of E is what? 1, 2 and 3, number of children. Now if I ask you degree of this tree, then what you can say? The maximum degree of any node, that is known as degree of this tree. So the maximum degree in this tree is what? 3 only, right? Because no node is having more than 3 children. If I ask you degree of this tree, then what you can say? The maximum degree of any node, that is known as degree of this tree. So the maximum degree in this tree is what? 3 only, right? Because no node is having more than 3 children. So the maximum degree is 3. So you can say degree of this tree is also 3. So next is depth of a node. Here I have written sibling and what is degree, right? Now depth of a node is what? See, the length of the path from root to that node. Now how to find out the length of the path? See, now path is what? As we have discussed, it is sequence of consecutive edges, right? So in the simple terms you can say what is depth of a node? Number of edges from root to that node. As simple as that, right? Now if I ask you what is depth of F, fine. So find out the number of edges from root to this node. So root is A, number of edges from root to this node is what? 1 and 2. So depth of this is what? 2, simple, right? Now if I ask you depth of J, find out the, first of all, path from root to this node is this one and this one. Number of edges are 1, 2 and 3. Just count the number of edges from root to that node. So this is what? The depth of J is what? 1, 2 and 3 only, right? Depth of D is what? Only one edge I have from root to this node, that is 1 only. Now what about depth of A? That is 0, because from root to A is only the root node, na? So there is no edge from root to this one. So the depth of root node is what? 0 always. Discussed, it is depth of E, F, G, H at this level. Depth of all these 4 are what? 2. Depth of all these 5 are what? 3. Now next is height of a node. See, if I ask you what is height of G, right? So height means from here, from bottom we will calculate the height. So from G you need to check out the path to its leaf node. G is having 2 leaf nodes only. So path is what? G to L, G to M. Both are having how many edges? 1, right? Same edges. So the height of G is what? 1. Now if I ask you height of B, just find out the path from that node to its leaf node, right? Or you can say to its deepest leaf node, or you can say the longest path you have to find out, right? So now from B, see the leaf node are F also, but the path is having only 1 edge. So this is 1 edge. From B to I, 1, 2, 2 edges are there. From B to J we have 1, 2 edges are there. From B to K also we have 2 edges, and here I have 1. So the maximum is what? 2 only. So the height of B is what? 2, right? So you have to find out the number of edges in the longest path from that node to a leaf node. right? The longest path you need to take care. It's not like that it is also leaf node, so the height of this can be 1. No, because the longest is what? 2. Longest path is what? 2, having 2 edges. So the height is that one, right? The maximum distance we will take from that node to its leaf node. Now, see the height. Height and depth of a leaf node, right? Yes, sir. Or from root, sorry, from C to leaf nodes. So from C, path from that node to its leaf node, right? Or you can say to its deepest leaf node, or you can say the longest path you have to find out, right? So now from B, see the leaf node are F also, but the path is having only one edge. So this is one edge. From B to I, 1, 2, 2 edges are there. From B to J we have 1, 2 edges are there. From B to K also we have 2 edges, and here I have 1. So the maximum is what? 2 only. So the height of B is what? 2, right? So you have to find out the number of edges in the longest path from that node to a leaf node, right? The long longest path you need to take care. It's not like that it is also leaf node, so the height of this can be 1. No, because the longest, the distance of this G from root is what? The path is this one and this one. How many edges are there? 1 and 2. So the level of G is what? 2. Level of L is what? 1, 2 and 3. Or here you can say each hierarchy or each step is known as level. See, this is known as 0th level. Next level is this one, B, C and D. This is what? Level 1. This is known as level 2. This is known as level 3, right? And this level of a node is always equal to depth of the node, and or as well as level of a tree. See here, the level of this tree is what? 3. How many hierarchy? What? This one, this one, this one and this one. But this is what? 0th level, and the maximum is 3. So the level of this tree is what? 3. So you can say level of tree is equal to height of the tree. Height of this tree is also 3. How you will calculate the height? Number of edges in the longest path from that node to leaf node. And height of this tree is what? Just find out height of the root node. Height of the root node is what? 1, 2 and 3. The longest path is having 3 edges. So you can say level of a tree is equal to height of a tree. But level of a node is not equal to height of a node. And level of the tree is also equal to depth of the tree. And level of a node is equal to depth of a node. Right? You can check out this also with this example. Fine. Now I guess I have discussed all the terminologies used. Minus 1 edges. Here also you can count the number of nodes as well as the number of edges. That is the condition, right, of a tree. N nodes means n minus 1 edges should be there. And if you will add one more edge, it means it will form a cycle. But in a tree we cannot have any cycle. It should be acyclic. right? Now I have C, right? And in C, suppose this is what? The right child, right? So here I have F, but in the left I don't have anything because there is no left link or this nodes cannot represent a tree in the memory, something like this, right? So how we are going to represent that, this tree into the memory? See now here basically we will discuss about binary trees. It means a tree can have at most 2 children. So how you are going to represent this binary tree actually, how you are going to implement this one? See, these are nodes. So how we are going to represent a node here? Dynamically, obviously we are going to create a node. So this is what a data part which is containing this data, as well as 2 links are there. One is link, means one link, left link, this will contain address of the sub this left subtree. This is going to contain address of this subtree, right? Or you can say root of this subtree and root of this subtree. So 2 links would be there. This is what you can say left link, or this is what right one, right? Now here also we are having what? We are having data B. B is also having 2 links. So here we have what? D, and here we have what? E. But here we don't have anything because D is not having any child node, E is also not having any child node. So here in the left and right link we will store null only, right? Here we have C, right? And in C, suppose this is what? The right child, right? So here I have F, but in the left I don't have anything because there is no left child. So here you will store null, here also we will store null. This is how we are going to actually implement the tree. These are nodes, right? Now how you will write down in the code? See how you are going to create this node. This thing we have already discussed when we were discussing the linked list. Obviously we are going to dynamically create this node. So we are going to use what? Struct. The name is what I am taking, node, and here I am taking 3 parts. One is data part, next is 2 links would be there, one is left and one is what? Data. So it is going to implement that file system. In file system also we store data something like this. Here we have directory, then we have subdirectories, then we have file. So this is what? A hierarchical form na. So trees are used to basically implement this model, that file system, right? In routing protocols also we are going to use tree data structure. Next application may be it organize the data for a quick search or insertion and deletion, like you can say as a binary search tree, heap tree also, right? So there are many applications of tree. One by one applications also we will discuss in later videos with the implementation. So now in next video we will discuss types of trees. That you can say brief introduction of types of trees, binary search tree, AVL tree and all that. After that we will discuss those trees in details. So I'll see you in the next video. Till then, bye bye, take care. In this video we are going to talk about binary tree, its properties and its types, right? In the previous video we have discussed what is a tree, and you can say that in this video we are going to talk about binary tree, its properties and its types, right? In the previous video we have discussed what is a tree, and you can say that introductory part of trees, right? Right, some basic basic terminologies which are used in tree, as well as how to represent a tree, the logical representation of a tree, right? 0, this is what level 1, this is what possible. Now see, is this a binary tree? This is not a binary tree, because see here in this case, this node is having 3 children. That is not possible. We can have at most 2 children. So this is not a binary tree, right? All these are binary trees. This is also a binary tree, right? Now if I draw something like this and this is also a binary tree. The only condition is what? Each node must have at most 2 children. If this condition satisfies, that is a binary tree. Now how we are going to represent this binary tree in memory, that thing we have already discussed in the previous video. See here, this is the node. Each node is having what? Information plus may or may contain links. That is not compulsory that each node should contain links. 4 is having both left and right child. So this is left and this would be right. Right? Here we can have 5 and here we have 5 and 6. Both 5 and 6 are having no children, so the links would be null. Right? This is how we are going to represent the tree actually. This is just a logical representation of a tree. How we are going to store the tree in memory, we are going to dynamically create these nodes, we are going to set these links. That thing also we will discuss, the implementation of binary tree, right? Now next thing is, see now some properties of binary tree. See, we have discussed what is a level in the previous video. This is node, this is what level 0, this is what level 1, this is what level 2. Now at any level, see, at suppose I am taking at level 1, how many maximum nodes can be possible? See, at level 1 only 2 nodes can be possible, maximum nodes. Here we cannot have 3 nodes because at most 2 children can be there. Now at level 0 the maximum node possible is only 1, right? At level 2 the maximum node possible are, see the maximum node can be, here I have 2, here also I have 2 and 2 children of this node. So this is what level 2. At level 2 we can have 4 children maximum, we cannot have 5, 6 or something like this, right? This thing I guess you are getting my point. Now suppose I am increasing one level, at this level, at third level, the maximum number of children possible are, maximum means each of this node at level 3, each node will have 2 children. So here I have 8 nodes, so 8 into 2, that is 16 can be possible. So at level 4, 6, suppose I have 3 levels only. Now height of this tree is what? Height of the root node is equal to height of the tree. Height of root node is what? 1, 2 and 3. Go to the longest path, find out the longest path. Plus at this level I have 4, plus at this level I have 8. It means you can say 14 number of nodes, right? Maximum number of nodes. Fine. Now if I say height is only 2, right? Height is 2 means I am removing this level, means now height is 1 and 2. Height of root is 2, so height of tree is also 2. Now if height is 2, maximum number of nodes possible are 1, 2, 3, 4, 5, 6, 7. So how to calculate maximum number of nodes? If height is h, simply you will add all the maximum number of nodes at each level. So you can say 2 raised to power 0 at this level, 2 raised to power 1 plus 2 raised to power 2 plus 2 raised to power 3 and till 2 raised to power h. Now this is what? Simply a GP series, and how to find out the sum, you can easily Google it out. I am not going to tell you this thing. So answer of this would be 2 raised to power h plus 1 minus 1, right? So maximum number of nodes of height h, I am talking about this binary tree, right? So maximum number of nodes can be h plus 1 minus 1, right? And if I ask you the minimum number of nodes, if height is h, then see, minimum number of nodes can be h plus 1. How? If height is this one 0, it means height is 0 means we have only one node, right? We don't have this thing, we have only one node, it means height is 0. So the minimum number of node is 1. If height is 1, see, this is height 0, this is a tree, binary tree having height 0, minimum number of node is 1. Now if height is 1, I am going to increase the height. Now height is 1, height of this tree is what? 1. Minimum number of nodes are 1 and 2 only, minimum number of nodes. I am not adding this node, second node, right? Now if you increase the height one more, suppose I am increasing height one more. Now height is 1 and 2. Now height is 2 and minimum number of nodes are 1, 2 and 3. If you will increase one more height, now height is 1, 2 and 3. Height is 3, minimum number of nodes possible are 1, 2, 3 and 4. So you can say minimum number of nodes possible are h plus 1, h plus 1, h plus 1, 3 plus 1 is 4. If height is is 1 means this one height 1, 2, two nodes are possible, means h plus 1, minimum number of nodes are possible, right? Next thing is, if suppose you are given maximum node, minimum nodes and you are supposed to calculate the height, you can say the maximum height of the tree possible and minimum height of the tree possible, n plus 1 minus 1, and here we are taking the 1. So this can be n minus 1 can be what? Maximum height n minus 1 and minimum height can be this one, log 2 n plus 1 minus 1. Now we will see types of binary tree. So type and minimum height can be 3. See, the definition is what? It is a binary tree where each node contains either 0 or 2 children, or in another term you can say it is a binary tree. See, of course, obviously it is a binary tree, plus one more condition is it is each node is containing either 0 or 2 children, or you can say each node will contain exactly 2 children except leaf node, right? Now see, what is a full binary tree? Now if I draw something like this, is it a full binary tree? Yes, because it is a first of all a binary tree, plus here each node is containing either 0, see this one is containing 0, 0 and 0, means these are leaf node, right? Or 2 children, this is containing 2 children, this is having 2 children. So this is what a full binary tree. Now See, this is what? Is this a full binary? In this video, we are going to talk about binary tree, its properties and its types, right? Minimum number of nodes are 0 children. This thing you need to find. So in this video, we are going to see how to implement a binary tree. We are going to actually write down the code for the implementation of binary. Create is going to true. Fine.